Now there is yet another representation, or I should probably call it a class of representations, that is called the data flow graph. A data flow graph in some ways is a generalization of the idea of what these architectures are, right. Why I am saying that it's a probably called a, you can call it a class of representations, is because the core concept of a data flow graph is adapted for many different things. You are no longer restricted to something like FIR filters or even signal processing algorithms. Anything which has a so-called data flow nature can be represented using data flow graphs, and more importantly, people have come up with many variants of data flow graphs that are useful in different contexts. Okay. So I am going to sort of present a very simplified basic version of the core idea of what a data flow graph is, but keep in mind that when you are looking at the literature, you might come across different variants of this, right, which are used in different contexts. So a data flow graph essentially for the same problems, right, the FIR and IIR filter would look something like this. I would say that over here I have a concept of something called actors, okay. They are sometimes also called nodes or vertices in the graph, right, and there is the concept of firing or execution of these nodes. So an actor firing essentially means that it does some work and it probably consumes some input, does some work and generates output, okay. That is the core idea of data flow. It essentially says that you have several actors that have inputs, they are waiting for something to appear on their inputs. As and when those inputs arrive, they consume them in some way, do something with those inputs and generate outputs, okay. An example of this for the case of the IIR filter would look something like this. There is one actor which I will mark as S, which is a source, right, and this source essentially produces the x of n as outputs, okay. Where does that go? It goes to an adder, and the output of this adder gets fed back over here, multiplied by two things, or rather multiplied, no, okay, sorry, let me correct that. Over here we explicitly make the multiplication as an execution, an event, and the D on that arc represents that there is a sample delay on that arc, okay. So this effectively, now I am not really showing explicitly where the output is, but you can sort of see that, you know, this is Y, right, this one produces X and over here we have Y as the output. I am not having a separate sort of node to indicate that this is the output node or anything of that sort. Similarly, there is no explicit input node except that the S, the source itself, indicates that it can generate outputs, okay. Now the one interesting thing about this data flow model is that it sort of can now be thought in terms of a sequence of actor firings, right, and the whole idea of how is a computation being performed repeatedly can then be encoded as a sort of sequence of firings of the different actors that are involved, okay. So what I am going to do is in fact give these actors slightly different names. I will call this A, M, and this one can remain as S, okay. The idea behind data flow is that it says at any given point in time I can look at all the different actors, decide which ones of them are ready to execute and execute them, okay. Of course, how do I execute them, where do I execute them, am I going to run it on a processor or in some custom hardware? That is not the concern of the data flow graph representation. The data flow model itself is just saying that this is how you can sort of understand the meaning of this graph and how it evolves in time, okay. So what we say is that there are multiple firings of each of these nodes, and a firing sequence would look something like this. I could say S0, S1, S2, etc. And what I implicitly mean by this is generating x of 0, this is generating x of 1, this is generating x of 2, and so on. Okay, every time that S fires, it generates a new value of output, x. Okay, so S could have this firing sequence, S0, S1, S2. I mean, the sequence is implicit. It is always going to be ascending numbers, S0, S1, S2, it has to be numbers like that. The question is, in the meantime, what do A and M do? Okay. Now, how an actor fires when it is ready to fire is determined by the state of its inputs. Okay. And the basic data flow model, or one of the models, which is basically called synchronous data flow, right? This is a variant of something called the synchronous data flow model, right? Essentially what it says is, every actor looks for certain number of for something tokens on its inputs, and if it has sufficient number of tokens, it can fire, consume those tokens and generate something at its output. Okay. Now, what does a token look like, and how do you determine whether an actor is ready to fire or not, right? You can think of a token either, in this case, for the S, the source, it does not need any tokens for the simple reason that it does not have any inputs. So the assumption over there is that a source that does not have any inputs is always ready to fire. Okay. But among the two other actors, A and M, the question becomes which one is ready to fire, and how do I decide that? Okay. Let's look at A. A is an adder, it has one input coming from S and another input coming from M. Okay. As of now, I don't see anything on its inputs. There is nothing there to indicate that A is ready to fire. What about M? It has one input which is coming from the adder, and the way that I have drawn this diagram essentially says that that input arc has a delay token on it. Okay. So this is essentially what I mean by a token. Why is it a token? You can think of it in some ways as an initial condition, right? Because think about what we are saying, y of n equals A times y of n minus 1. In order to compute the value of that equation, I need to have some initial condition. I need to know that at t equal to 0 or t equal to minus 1 or some arbitrary t, what is the value of y? Only then I can proceed from there. Okay. So effectively this d that I put over here, this token, is sort of saying, okay, these are the initial conditions. And with these initial conditions, you can now start to evolve. Your data flow graph can now start to evolve. Okay. How does it evolve? One step in this would essentially be, this one can generate a token out here. Okay. At any point in time, it can generate tokens. So it can generate 1D, 2D, 3D, 4D, doesn't matter. You know, in principle, I can have an infinite number of Ds on this particular arc, the one from the source to the adder. Right, but I am going to assume that it just fires once, produces 1D, okay, and in the meantime M also fires. What does it do when it fires? It basically consumes that initial value and generates a token on its output. Okay. Now, if I look at the new state of the graph, it essentially corresponds to this. Right. And now what I am saying is, if I look at all the different nodes in the graph and try to find out which ones of them are ready to execute, right, which ones would I say are ready to execute at this point? Which ones have tokens on their inputs, so to say? A has enough tokens. On all input arcs, it has tokens. Okay. What about M? M does not at this point. Okay, so M is not ready to fire. S is always ready to fire for the simple reason that it does not have an input, therefore it does not have any dependencies, okay, which basically means that I can then go from this to a next state where A fires and what happens when A fires? It consumes tokens from both of these inputs, right, and produces an output D over here, okay. So what is the sequence of firing that has happened? Effectively, I have had this sequence which basically says S0 fired over here and M0 also fired. After that, over here A0 has fired, okay. So after this sequence S0, M0, A0, the graph is now back to its original state, because if I look at it, these two are exactly the same, okay. So effectively what I am saying in other words is that sequence S0, M0, A0 returned the graph to its original state. Okay. This is considered one iteration of the entire graph. Okay. All the functions or the actors in this graph have fired once and brought it back, and have fired once, that essentially is counted as one iteration of the graph. Has it returned back to its original state or not? In this case it has, right? But what I want to impress upon you is it was not necessary that it actually returns any sequence of firing. It is not always necessary that it brings it back to a known state, right? Because let's look at it. Was this the only possible firing sequence that we had? No, I could also have gone in the sequence M0, S0, A0. This is also valid. Right? What about S0, S1, M0, A0? This is also valid. Why? Because S doesn't have any dependencies, it can fire as many times as it wants. Okay? The problem here is graph has not returned to the original state. Why is that? Because essentially what we are saying is this was S, A, M. After all this firing, I will end up with this state. This was the original, and this is after S0, S1, M0, A0. Right? So there is this difference over here. But it's not a major difference, it's just that one extra token is there on the SA arc, right? But you can see how this is useful. Effectively what it's saying is I can now consider how to sort of think in terms of an iteration of a graph and say, okay, you know, by running through these steps, I can basically finish one round of computation. In this case, one iteration through this graph will result in one new value of y of n being produced. The next iteration will produce one more output y of n. The next iteration will produce one more output y of n, and so on. Okay? The order in which the actors execute in order to complete that iteration is not important as long as the rules of the execution are being followed. Right? As long as I make sure that any actor can fire only when there are sufficient number of inputs, the order in which I do it does not matter. okay, and that is the crucial point of the data flow graph. It essentially is able to capture precisely what the dependencies between the different actors or the computations in the graph are, and then allow you to figure out how to actually perform those computations. Should they be done on limited amount of hardware, on a single processor, on a dual processor system, which operation should go where, all of those things you can experiment with much more easily once you have this data flow model in place, okay. And we will be making extensive use of this in order to understand data flow as we move forward, understand the executions or the conversion of our algorithms to hardware models or to software implementations as we move forward. Yeah.
So I didn't understand what exactly the position of token has changed.
Yes.
Won't this change how the circuit will be made?
So, okay, first things first, a data flow graph does not necessarily directly imply a circuit. It could be software, right? So, an actor in a data flow graph can be a function call inside a C program that you are writing, okay. And why is that useful? I mean, you might think that that's overkill. I mean, why would I ever bother to use actors and this kind of a model over here? It becomes useful when you are talking about multi-processor systems, where I could have two processors, for example, and each one of them can pick which actor is ready and immediately execute it when it's available, okay. So that's the first thing to be clear about. This does not, even though I'm drawing it in terms of visually, there are nodes and there are arcs between them, that does not mean there is a physical circuit that is implementing this. It could be software. Now the second thing is, all that I'm saying by a valid sequence is something that does not violate the requirements of data flow, okay. One way to understand that would be, what is an invalid sequence? So in this case, an invalid sequence would be starting from the original, right? A0, it's already invalid, okay, because A is not ready to fire right at the beginning of the circuit, okay. I could go further and say, all right, supposing I do S0, M0, A0, fine, so far so good. A1, again invalid, it has become invalid at this point, okay. S0, S1, M0, M1, invalid, okay. So the point is, why is this invalid? Because for M1 to execute, A0 should have completed, only then I'll get a token back at the input of M, okay. So all of these are examples of invalid sequences, right? That's all. So all that I'm saying is, as long as the rules of firing, there should be a token present on the input, on every input, and the firing itself will take one token out of each of those inputs and generate a token at the output. As long as those conditions are satisfied, the sequence is valid, which means that there are essentially an infinite number of valid sequences that you can go through over here, right? Now, why is this useful? We will get to it later when we start talking about scheduling data flow graphs onto various kinds of hardware.